Hello, welcome to another lecture in the course on 3G, 4G wireless communication systems. In the last lecture, we had looked at the distorting effects of the carrier frequency offset on the OFDM system, that is when the transmitter oscillator and the receiver oscillator are not synchronized, that is there is a frequency offset. What is the impact of this frequency offset? That is what we characterized in the last lecture. We had said that because of the presence of a spurious carrier frequency offset, there is a loss of orthogonality at the receiver in the OFDM system, which results in inter-carrier interference, that is inter-subcarrier interference. So, now we have a signal component in the received signal plus an interference from the adjacent subcarriers plus the usual Gaussian noise as is shown here in this slide. Hence, the signal to noise power ratio now can be characterized using the signal power to the interference plus noise power. Hence, we have an SINR, that is signal to interference plus noise power ratio at the receiver. And in the last lecture, we had actually developed a model to characterize this signal to interference plus noise ratio at the receiver. We had seen that the SINR at the receiver can be characterized as follows, that is signal power, which is P magnitude h square, that is average channel gain, into sin pi epsilon by pi epsilon whole square, where epsilon we said is the normalized carrier frequency offset, divided by 0.822 P magnitude h square sin pi epsilon square plus sigma n square. The numerator is the signal power, the denominator is the intercarrier interference, that is the interference power plus the white Gaussian noise power. Alright, so as you can see, the interference power adds to the noise power, which results in a net degradation in the SNR. In fact, we had looked at an example and we had said for a simple case with about a 5% carrier frequency offset, the reduction in SNR is close to about 17.5%. And then we had started looking at the PAPR issue, that is the peak to amplitude power issue in this OFDM system. Right, we said PAPR stands for peak to amplitude power ratio, and we had started looking at a PAPR of a conventional single carrier system, where with BPSK and amplitude level A, we said the average power across symbols is A square, the peak power is A square because each symbol is plus or minus A. Hence, the peak to average power ratio is A square divided by A square, which is close to, which is 1. Practically, in practical systems, it is close to 1, it is essentially 0 dB. Hence, there is not a significant deviation of the power of the instantaneous power level over the average power. Hence, what we are saying is the swing is not very large over the mean power level. Now, we want to carry forward this discussion and look at how the peak to average power ratio looks in an OFDM system. Remember, this is the PAPR peak to average power ratio in a conventional single carrier system. How does it look in an OFDM system? That is what we want to look at next. So, right now we want to start by looking at a PAPR of an OFDM system. So, consider, so PAPR in OFDM system. Now, in OFDM, remember, we are not transmitting the symbols as is, but we are loading the symbols onto the subcarriers, and then we are taking the IFFT of these symbols before transmitting these symbols. So, we are considering the IFFT of the symbols. All right. So, in an OFDM system, the information symbols x0 x0, x1, x2, let the information symbols be given as some plus or minus a, plus or minus a, plus or minus a, and so on. Now, these information symbols are actually loaded onto the subcarrier symbols, subcarriers. So, these these information symbols are loaded onto these information symbols, they are loaded onto the sub carriers. Alright. Hence, the transmitted symbols are x0, x1, small x0, small x1 up to small x1 minus 1, which are actually the IFFT samples of these information symbols. So, what are we doing? We are taking these information symbols which is we are taking these, remember in an OFDM we are taking these symbols x0, x1 up to xn minus 1, and we are performing an IFFT on these symbols to yield the small x0, small x1 up to xn minus 1. So, we are taking these capital X's which are loaded onto the subcarriers and forming these IFFT samples. So, these are the information symbols, and these are the IFFT samples of the information, and these are the IFFT samples of the information symbols. Hence, the transmitted samples are this x small x0, x1, xn minus 1, which are the IFFT of capital X0, x1, xn minus 1. Hence, the transmitted or the transmitted samples are x0, x1 up to xn minus 1, which are the IFFT of the information symbols, or which are the IFFT samples of information symbols. IFFT samples of information symbols, capital X0, capital X1. So, in OFDM, as we are very well familiar, we are not directly transmitting the information symbols, but before transmitting the information symbols, we are performing an IFFT operation over these information symbols, and we are then transmitting the IFFT samples. Alright. So, this is what we already know about an OFDM system, that is in the sense that we are not transmitting the symbols themselves, but we are taking an IFFT operation before transmitting the symbols. Hence, the symbols are given as the x, or the samples are given as the kth sample is given as summation 1 over n, which is essentially the IFFT, the n point IFFT, I equals 0 to n minus 1 xi e to the power of j 2 pi ki over n. So, these are the information symbols and this is the kth IFFT sample. These are the information symbols, and this is the kth IFFT sample. Okay. And the average power is given as now. So, now what we want to see is we want to characterize what is the mean to average power, that is the peak to average power ratio of these transmitted samples, because we are not directly transmitting the information symbols. So, we want to characterize what is the peak to average power characteristic of whatever is being transmitted on the medium. How does that How does that look like? That is what we are essentially interested in characterizing. So, let us look at the average power of this thing. What is the average power? What is the average power? The average power is nothing but expected magnitude x k square. That is nothing but 1 over n square summation I equals 0 to n minus 1 expected magnitude x I square from the above into expected magnitude e power j 2 pi k I by n whole square. Now, we know that expected magnitude, this is simply a phase factor, that is expected that is e power j 2 pi k I by n is simply a phase factor. Expected magnitude e power j 2 pi k I by n square is in fact this is 1. Hence, this is nothing but expected magnitude x k square is nothing but 1 over n square summation I equals 0 to n minus 1 expected magnitude x I square. This is nothing but, remember, each x I square, in fact each x I is an information symbol that is plus or minus a, since expect x I magnitude x I square is nothing but a square. Hence, this is nothing but 1 over n square sigma I equals 0 to n minus 1 into a square, which is 1 over n square into a square into n equals a square over n. Okay. Hence, the average power, hence the average power of transmission hence the average transmission power in this system is a square divided by n, that is the average power. But how does the peak power look like in this system? How does the peak power look like in this system? In fact, what we are going to find is that the peak power can be significantly higher. Let us look at the peak power in this system. For instance, let us look at every sample. Let us look at one specific sample. Let us look at the 0th IFFT sample, which is 1 over n summation I equals 0 to n minus 1 xi e power j 2 pi I times 0 divided by n, because we are looking at the 0th sample, which is nothing but 1 over n summation I equals 0 to n minus I equal to 0 to n minus 1 summation of x I. All right. This is sort of this is essentially the component at transmitted, the sample transmitted corresponding to time 0. Now, let us consider a case in which all x i's are actually equal to, that is, there can be each x I is plus or minus a with probability half. Let us consider a scenario to characterize the peak power where all x i's are actually equal to have the same sign and are equal to plus a. So, let us consider a scenario where x 0 equals x 1 equals so on equals x n minus 1 equals plus a. And then what do we find? We find that x 0, in that case the small x 0 equals 1 by n summation I equals 0 to n minus 1 x I is actually 1 over n summation I equals 0 to n minus 1 of A, which is actually A. Hence, the peak power or the instantaneous power equals A square. Now, let us look at the result below. Before it says the average power is A square over n, the peak power is A square, hence the peak to average power ratio, hence peak to average power ratio hence the peak to our average power ratio or PAPR is nothing but A square divided by A square divided by n, which is equal to n. Hence, this means that the peak to average power ratio, remember in a single carrier system it is close to 1, in an OFDM system is very high, because remember the n, the number of subcarriers, can be as high as 1024, which means there is a significant deviation of the instantaneous power or the peak power about the mean. Hence, PAPR in an OFDM system can be hence the PAPR of an OFDM system can be significantly higher, that is, there is a significant swing of the instantaneous power or the peak power with respect to the mean power. Hence, there is a significant swing of the instantaneous power with respect to the peak power. Further, what we observe here is interesting. It says that this peak to average power ratio, that this rises with n, which is the number of subcarriers. Hence, the peak to average power ratio, hence or further the PAPR rises with n, that is the number of hence the PAPR rises with capital N, which is the number of subcarriers, and this is a key observation, which is the PAPR increases as the number of subcarriers increases, and this is a problem, which is a high deviation of the peak. And why is this arising? Why is this high PAPR, or why is this high deviation of this peak power with respect to average power arising? That is arising because of the IFFT pre-processing. Normally in a single carrier system there is no pre-processing. However, in OFDM, because of this IFFT pre-processing, we are actually enhancing the instantaneous swing of these transmitted symbols over the average level. Hence, the high PAPR in an OFDM system essentially arises because of the IFFT operation. Because of the IFFT operation, where data symbols across different subcarriers can add up to produce a high peak value signal. This arises because data symbols across subcarriers can add up to produce a high peak value signal. So, the PAPR is essentially arising out of the IFFT operation in Ofdm, and why is it arising? Because remember, these different symbols loaded onto the subcarriers are random, and depending on their nature they can occasionally all add up across the subcarriers to produce a high peak value that gives rise to a very high instantaneous swing with respect to the normal mean value. For instance, in an OFDM system with about 512 subcarriers and BPSK modulation, this swing can be as high as 10 dB. For instance, in an OFDM system with 512 subcarriers and BPSK modulation and BPSK modulation, the PAPR of the output can be as high as 10 dB. For instance, in an OFDM system with roughly about 512 subcarriers and BPSK, the PAPR can rise as high as 10 dB, that is 10 times peak power compared to the average mean value, which means a significant deviation of the peak with respect to the average value. And how do we represent a PAPR? How do we characterize the PAPR comprehensively? We characterize the PAPR of a system using the CCDF function or the complementary cumulative distribution function. Hence, the PAPR of an OFDM system is characterized using the CCDF. The CCDF function, that is the complementary cumulative distribution function, that is the complementary cumulative this is characterized using the complementary cumulative distribution function. What is the complementary cumulative distribution function? Let us consider a random variable x. The CCDF, which is denoted by f bar x of f of x, is simply the probability that x, which is the random variable, in this case we can consider it PAPR, x is greater than this value small x. That is, this x can be this random variable, which is essentially the PAPR. Remember, because the symbols are random, so the instantaneous power or the peak power is random for a group of symbols is random depending on the combination of symbols. Hence, it is a random variable, it is best characterized by a distribution function. Here we are using the complementary cumulative distribution function. You might be familiar with the cumulative distribution function, which is essentially the probability that x is less than capital X, and that starts from 0 and goes to 1 from the properties of random variables you might be familiar. The CCDF on the other hand is simply 1 minus the CDF, which is the probability that x is greater than capital X, and that starts from 1 and slowly goes down to 0. That is, for higher values of the probability that a random variable is greater than larger values is progressively smaller. So, the CCDF, if you plot the CCDF, a typical CCDF looks like this. So, this is a typical CCDF. It starts at 1 and progressively, of course, it goes down to 0. Alright. So, it starts at 1, progressively goes down to 0, and that is the probability that x is greater than x. In our case, it means what is the probability that PAPR is greater than a certain threshold. So, that characterizes, and we want this curve to progressively be towards that is, we want the PAPR to be as close to 0 dB as possible. That is, ideally we would want this PAPR to look like this. This is the ideal PAPR characteristic of in fact of single carrier system. That is, PAPR is exactly 0 dB, that is probability, if probability 1 it is less than 0 dB, and with probability 0 it is greater than 0 dB, that is, it is always exactly 0 dB. That is what we want, the ideal, but in practice, especially in OFDM systems, we see that it has a high PAPR value which significantly deviates from the 0 dB ideal desired characteristic of the PAPR value. For instance, this plot here, it shows the PAPR of OFDM systems for several different subcarriers, that is the PAPR for n equals 64, for n equals 128, n equals 256 and so on. As we see the number of subcarriers increases, the PAPR gradually increases. The way to read this plot is as follows. For instance, let us say we want to find the PAPR corresponding to n equals 1024 subcarriers, and I want to do it for a level corresponding to 9.5 dB. For instance, here I draw this line at 9.5 dB, approximately 9.5 dB. What we see is the probability that the PAPR with n equals 1024, the probability that the PAPR is greater than 9.5 dB with n equals 1024 subcarriers is 10 power minus 1, that is 0.1 or 10% probability that the PAPR is greater than 9.5 dB. Similarly, the probability that the PAPR is greater than 11.5 dB is 10 to the power of minus 3 or 0.1%, so on and so forth. So, given a number of subcarriers, what you can find from this is what is the probability that the PAPR is greater than a certain threshold. In fact, the farther this curve is to the right, the higher the PAPR is. All right. In fact, if you want to look at what the average PAPR is, all you have to do is you have to look at the 50% point. That is, for you look at this point here for the n equal 1024, and you will see that the PAPR is 10 dB. That is, 50% probability, with 50% probability, this is the median, with 50% probability the PAPR is actually greater. I am sorry, this is not the 50% point, the 50% point is the 50% point. It says with 50% probability the PAPR, this is roughly let us say 8.5 dB. It says that with 50% probability the PAPR is actually greater than 8.5 dB, alright. So, that is the median point for this PAPR distribution, which can be obtained from the PAPR CCDF function. Okay. So, that is the importance of the CCDF of this PAPR function. So, coming back to our PAPR discussion, now let us talk about why this PAPR is such an important quantity in OFDM system. What is the problem with PAPR? What is the problem caused by PAPR? That is what we want to understand. What is the effect of PAPR on OFDM? What is the effect of this PAPR on OFDM system? For that we have to understand a little bit about what is the characteristic of these different devices in the transceiver. If you look at specifically, if you want to look at the amplifier, every amplifier has what is known as an amplifier characteristic. So, if you have an amplifier, it looks as like amplifier characteristic, which shows with respect to the input voltage what is the output voltage. Okay. So, with respect to, so this is the amplifier characteristic. This is the amplifier characteristic, this is the input voltage and this is the output. And this is the output voltage. Now, remember the amplifier, the ideal amplifier characteristic looks something like this. The ideal amplifier characteristic looks something like this. This is the ideal which is no matter what input voltage you provide, the output voltage is a scaled version of the input voltage, that is it is amplified and a scaled version of the input voltage no matter what input voltage you provide. But in practice typically the linear characteristic, this is what is known as the linear region, the linear amplifying region, this is the linear range. The linear amplification range of any device exists only over a certain voltage range. If the input is larger than that voltage rate, what happens is the output is no longer linear, but the output is non-linear. We say that this region, that the amplifier is saturated. This is known as the non-linear or the saturation region of the amplifier. This is the non-linear saturation region of the amplifier. Now, typically our amplifiers or typically the amplifiers in systems are biased around a certain operating point. This is the bias or it is biased roughly in the middle of the linear range, which is also known as the dynamic range. This is also known as the dynamic range of this amplifier. Okay. Now, as long as the signal swing is limited to this dynamic range or this linear range, the input and output are linearly related. That is, around this mean, if the deviation is not extremely large, but around this mean, if the deviation of the voltage is small, then the signal is still confined to the linear amplification range, similar to an SC-FDMA system. However, because in an OFDMA system the peak can swing very the swing of the instantaneous power can be very high compared to the mean, this crosses over into the non-linear range. This is in OFDM. The problem in OFDM system is, because we have non-ideal amplifiers in practice which have a limited linear amplification range, and the swing of the peak power can be very high compared to the mean, it crosses over into the non-linear range in which the amplification is non-linear, and once the amplification is non-linear, all the properties of OFDM cease to hold. That is, orthogonality is lost, there is going to be severe intercarrier interference, and so on and so forth. So, once the non-orthogonality aspect of this amplifier essentially comes in, because of the high swing in the peak power over the mean power, it crosses, the amplifier crosses over into the saturation region, hence the output is no longer linearly related to the input, which means OFDM properties cease to hold, which means the orthogonality is lost. Similar to a carrier frequency offset, you essentially have, that is similar to the distortion there, the orthogonality is lost. So, you have interference, and this interference in fact increases with the effect of non-linearity. It increases as the peak distortion, because as the peak swing increases, it crosses over more and more into the saturation region, which means significant distortion, significant intercarrier interference, which means again significant problems at the OFDM receiver, because there is a loss in the signal to noise power ratio. Hence, what we can say is, if the peak deviation in OFDM when the peak deviation about average is significantly high, the signal level moves outside of the dynamic linear range. Hence, when the peak deviation is high, the signal level crosses over into the non-linear or the saturation range of the amplifier. Hence, once the signal moves into the non-linear range, the amplification becomes non-linear, resulting distortion and intercarrier interference. Hence, high PAPR in OFDM system. Hence, high PAPR in OFDM results in amplifier saturation, in amplifier saturation, results in amplifier saturation, leading to non-linearity and essentially distortion and intercarrier interference. This leading to intercarrier interference. Thus, it leads to intercarrier interference, because essentially it results in loss of orthogonality. The non-linearity results in loss of orthogonality, which results in which leads to inter-carrier interference. Okay. So, now we want to see issues, or we want to see solutions to tackle this problem of PAPR. So, the main issue we want to address next is to tackle, that is how to tackle the PAPR problem, and for this specifically to tackle PAPR, a new technique is proposed in OFDM. This is termed as SC-FDMA. So, SC-FDMA is a variant of OFDM. It stands for single carrier frequency division multiple access. SC stands for single carrier, FDMA stands for frequency division multiple. SC-FDMA stands for single carrier frequency division for multiple access, and we say that, and SC-FDMA can be employed to combat the PAPR or reduce the PAPR. So, SC-FDMA can be employed to reduce PAPR in an OFDM. So, SC-FDMA can be employed to reduce PAPR in an OFDM system. Alright, so SC-FDMA is that technology which is a single carrier frequency division for multiple access technology, which is in fact employed in 4G. It is employed in LTE, that is long term evolution, which is a 4G wireless standard. In fact, it is employed in LTE to reduce specifically for this problem of PAPR, to address this high peak to amplitude power ratio, to solve this high peak to amplitude power ratio in OFDM, which otherwise leads to amplifier saturation and nonlinearity and distortion and intercarrier interference in OFDM. So, to understand SC-FDMA, let us go back and let us again take a look at how a typical OFDM transmitter looks like. Alright, so typical OFDM transmitter, that is how does the typical OFDM transmitter look? The typical OFDM transmitter has a serial to parallel demux and followed by it has a serial to parallel demux operation followed by an endpoint IFFT and then what we have is we have a parallel to serial mux operation or a multiplexing operation, and then we have the addition of the cyclic prefix as usual. Then we have the addition of the cyclic prefix. This is the typical OFDM transmitter. So, this is the serial to parallel, this is a demultiplexing operation, that is you make a block of symbols, you take the endpoint FFT, you take the parallel to serial and you take the cyclic prefix, and this we are saying this endpoint IFFT is creating a problem because this results in the signal here having high PAPR. So, this endpoint IFFT, this is essentially causing the this is essentially causing the high PAPR in OFDM. This endpoint IFFT, inverse fast Fourier transform operation, is essentially causing the high PAPR. This is essentially causing the high PAPR in OFDM, and we said this is a problem. So, to solve this, we slightly modify the OFDM transmitter as follows. So, the modified OFDM transmitter is follows. The modified OFDM transmitter is as follows. That will be the same as above, that is, first we take a block of symbols, that is, we perform the serial to parallel demultiplexing operation. Then we perform the n point FF, then we perform the n point FFT here. That is, before performing the IFFT, we perform an endpoint FFT. I will explain the logic for this shortly. And then now we give this, the rest is same as before, that is, now we perform the endpoint IFFT. We perform the endpoint IFFT, and then we perform the parallel to serial multiplexing operation, and then we add the cyclic prefix as usual, and then we transmit. So, this block here, this is the endpoint IFFT, which is the new block, or which is the change with respect to the previous OFDM transmitter. Now, look at what is happening here. If we look at the endpoint IFFT, and if you look at the endpoint FFT, and if you look at the endpoint IFFT, I am taking the endpoint FFT followed by endpoint IFFT, which means they both are inverses of each other, since they cancel. Now, so this has a cancellation effect. So, they can FFT and IFFT cancel out. So, the FFT and IFFT, they cancel out each other, which means whatever serial symbols that you input are the same symbols that are coming at the output, except for the addition of cyclic prefix. So, this looks like the same single carrier. So, the output here is essentially a single carrier output. So, output is a single carrier output, which means the PAPR is close to 0 dB, or PAPR is close to 1 or 0 dB. Alright, so by introducing this endpoint IFFT block, you are now essentially reducing this OFDM system to the earlier single carrier system. Alright. So, to reduce the PAPR, what can be done is an FFT operation can be introduced here. However, single carrier systems, of course, as we said, again we come back to the same issue, which is how to solve the intersymbol interference problem in this single carrier system. Hence, what we do is, as a trade off, we do not perform here an exactly endpoint FFT, but some m point FFT, where m is slightly smaller than n, so as to still not move completely towards a single carrier system, but retain some properties of OFDM as well as reduce PAPR. So, to achieve a trade off, what can be done is by introducing an FFT. Hence, what we realize is, hence PAPR can be reduced by introducing can be reduced by introducing endpoint FFT block, which converts the system FFT block which converts the system into a so the PAPR can be reduced by introducing an endpoint FFT block, which converts the system into a single carrier. It converts the system into a single carrier system. However, we do not want to completely move towards a single carrier system, but we want to retain the properties of OFDM also. Hence, instead of M, we use an M slightly, which is significantly less than M point FFT, so as to reduce the PAPR, at the same time retain the properties of OFDM system. However, instead of using an N point FFT block, one can employ an M less than N point FFT to reduce PAPR while still retaining properties of the OFDM system. So, M is less than N, that is the key, M less than N point FFT to reduce PAPR, while remember OFDM is very important to tackle inter-symbol interference, that is inter-symbol interference in this frequency selective system. So, we want to do an FFT to reduce the PAPR, but we still do not want to do a complete N point FFT, because that will move again towards single carrier system introducing inter-symbol interference. So, we want a trade off between these both. So, we are going to do an M point FFT, which is where M is significantly less than N. So, what is the proposed architecture? So, now we want to look at in detail the actual proposed architecture, that is what is. So, how does the proposed architecture, or how does the SC-FDMA transceiver transmitter schematic look like? So, we want to look at the proposed SC-FDMA how does the proposed SC-FDMA schematic look like? The proposed SC-FDMA schematic looks as follows, that is, I have a serial to parallel, again this is the demux operation that we had earlier, where we form a block of symbols, and now instead of directly doing the FFT, here we have some M. So, we have a smaller number of symbols. So, here we are going to do now N. So, we are going to take only M symbols instead of N. So, here we are going to do an M point Now, after we do this m point FFT, we are going to map these m symbols to n subcarriers. So, we are going to map these m symbols to n So, we are going to do a subcarrier mapping. So, we are going to do a subcarrier mapping, and now out of this subcarrier mapping, here at this point we still have this is m symbols. Now, after we do the subcarrier mapping, now here we have n symbols. So, we do m point, we take m symbols, we do an m point FFT, then we map to capital N subcarriers. Remember, we said m is much less than n. Alright, so due to the lack of time, I will stop here at this point, and we will continue again in the next lecture and complete this SC-FDMA transmitter schematic. Thank you very much.